I have to start the little thing. All right, welcome back. Today we'll talk about system calls, about the kernel structure overall, and of course about the homework solution and the next homework. Right, so I thought we'd start with a few clicker things again. Oh crap, what's it called again? iClicker. There we are. Ah yes, and I should have the control on my side. Okay, it's AA. And it's quit unexpectedly. All right. Let's try it again. iClicker is already running. All right, trying again. And it quit again. Okay, let's just ignore that then. Yeah, my questions weren't all that brilliant anyway. We'll revisit next time. I probably have to restart the computer and all that. I don't want to get into that. So last time we were talking about we got into the first system call. I think it was right. We were looking through the whole way. Today, I'll try to give a sort of a bigger overview of the whole structure of the kernel. There's a whole lot of files. It's not that many lines of code. Actually, let's take a look. So go to no. Let's see. And generally, if anything I'm doing on the screen seems unfamiliar, like, oh, I wouldn't know how to do that, figure out how to do it. Right? You see what I've been doing, but you'll have to kind of Google a little bit for it. And I've noticed in office hours and other times that some of you don't have all of the sort of skills that would be good to have to do well in class and generally to do well at UIC. Make sure you have a good editor, that you know how to use the command line. I try to push people to learn to touch type. That is, type without looking at the keyboard. It really is a revolution in your life if you get that. Well worth the pain that it takes. Anyway, so I just wanted to see how many lines of code is in there. I think virtually everything is in C, H, or S files. So there's some junk in there, but it doesn't matter. That's 11,000 lines. Okay, but actually, there's a lot of space and comments, that sort of thing. One kind of neat trick to get a better view in C code is to look for semicolons, because every line of C code will have a semicolon unless it's like a curly brace. And do we really want to count those? So, of course, it thought that was the end of the line. So that's 4,000 lines of actual, rough approximation, but 4,000 lines of functional code that makes the whole kernel. That's pretty cool. In fact, it's more than the kernel. It's all of the tools too. All of the tools, right? We have a few programs in there. All right. But before we get into that, let's take a brief look at the homework 2 solution. Who finished homework 2? All right. And who didn't even get started? Okay. You wouldn't admit that anyway, would you? All right, let's take a look. So I'll do this. In fact, I think just for posterity, I'm going to pause the recording a little bit when we look at the solution code. All right. So just to make sure. Good. So our next homework, may as well just take a quick look at that first, is going to be making some extensions to the kernel. At last, we dive into the kernel. In fact, from now on, there's not going to be so much assembly. We'll get back into assembly a couple times when we start switching processes and we implement threads, that sort of thing. But generally, most of it is going to be just more of low-level C. The coming homework here, we're implementing a couple of drivers, device drivers. So let's see. Actually, no. Let me overview let me draw a picture of the kernel for you first. Where are my drawings? Oh, I don't have any. All right. So picture of the kernel. I thought we'd do something like this. So we start out in boot asm. I need a little bigger. So I thought we'd. It's weird with this grid thing. Let's turn that off. Hold on. Unlock. Get rid of the grid lines. Okay, good. So when the kernel first starts out, right? It's not even the kernel when we're in boot asm, and then we get to entry.s. Oh, and the booklets. They're coming. I'm getting them tomorrow night, and so I'll hand them out on Thursday. For now, you can, if you like, you can get the booklet. If you just say make print in the master branch, you'll get a PDF of the booklet. But of course, it's all the same code, really. So you can just open up the files and look at them with your favorite editor, if you prefer. The booklet will be necessary primarily for exams. Oh, and I should mention now, for exams, you're allowed any notes you want in the booklet. Right? So there's no textbook in the exams, but you can write everything you want in the booklet during lecture and that sort of thing. That might help. You know, put little stickers and whatnot. Okay, so we go from boot asm to entry to main. So go like this. Let's see. So boot asm kind of loads all the code into memory, right? And it jumps to this entry point in entry.s, where we're still not really set up. Like, we're not even in 64-bit mode, I think, if I remember correctly. We certainly don't have paging enabled. There's all sorts of low-level assembly setup that's happening in entry. We'll take a look at that some other time. And then eventually we make it to main. You may have seen main already. There's all these calls to various initialization functions. Maybe we should take a brief look at that one now. All right, so it looks like that. All sorts of init, right? Make sure the console has white text and black background, and make sure that the timer starts going off in a regular interval, and any number of these little initializations. Clearing out a bunch of buffers, setting up the page allocator so that we can get free pages when we need them, and so on and so on. We'll look at this in a little bit too. But basically, main does a whole bunch of initialization, and toward the end of main, we get to, we call the, I'm just going to do it this way, scheduler. Oh. And from scheduler, there's a few steps in between, but really from the scheduler, we then just go like this. That's it. In terms of the kernel, it It runs the scheduler forever. All right, but there's something more going on. Usually when you start running the scheduler, immediately it'll find a process that needs running, start running that, and then the kernel isn't running at all. After that, the kernel does not run again until basically one thing happens. There's only one thing that can happen that brings us back into the kernel, and that is an interrupt or a system call, which are now implemented with the syscall instruction. It's essentially the same thing as an interrupt. Okay, so this is sort of the only straight line execution of the kernel. And then as soon as the first program, as soon as we call scheduler, some first program starts running, and that is init.c. That's our first program. All init does is really start sh, run sh, and if sh dies, run sh again. That's it. Okay, so how do we get the kernel to do anything? Well, that's through a bunch of system calls. So now there's like a separate little piece. We can call it the trap vector. Right, that gives us actually, yeah, okay. Let's go like this. All right, so during initialization, we've set up this little array, the trap vector, that says, oh, if a syscall instruction gets run, then you should jump to the address of this syscall handler, actually syscall entry. Or if some other trap happens, you should jump to this other trap handler. And then finally, the thing that really matters to us is we have another array, syscall array, where we support a bunch of different system calls. So let's go like this. Write, read, fork, open, and so on. Like this. And perhaps exit. Okay, so if a program wants anything done, all right, it's process is running, the init initially starts, it wants to run sh, well, it has to make a system call, so it calls sysfork. Now another program is running, right now it wants to exec something, it wants to start running another binary, it calls exec. And so on. So each of these are really the entry points where all the functionality of the kernel that we're interested in takes place. Right? Well, there's two places. There's the traps for when the timer goes off. It's the main thing, main interrupt we're interested in. And then there's all the various system calls that a program could initiate. So from our perspective, we need to look at how to implement a bunch of system calls, and that's what we'll do for this homework as well. Let's see. There's another way to draw this. I thought I'd do that too. So that's just sort of the flow, the instruction flow, if you want, the control flow, sort of how it's happening. But now there's these layers of the kernel as well. So we could call it sort of the system calls. And then we have in between, we might call this maybe the core. Let's call it the core. And this contains scheduler, file system implementation, memory allocator, sort of shared facilities that many system calls need in order to do their work? Oh, they need some memory. Right? Where are they going to get the memory from? Well, they have to use the shared memory allocator. Or they want to do something with the file system. There's a whole implementation of a file system. Actually, maybe I should call this the virtual file system. And then this here would be device drivers and file systems, really. All right. I would say that this is sort of a fair description of x86. So for every system call that comes in, there's some amount of work to kind of deal with the parameters, see if this is something that we actually should be doing, and so on. Eventually, we get down to doing the core work of the system call, and that's calling a whole bunch of the various functions in the core of the OS. But the core of the OS then relies on device drivers to handle multiple different devices. So if we want to do a system call write to a display, well, it's different than a system call write to a console or to a file, but in the end, sort of the core of the file, the core of the operating system handles it all the same, and eventually it gets down to the device drivers that do specific implementations for the little pieces that are different between different drivers. Same thing for the file system. Delete will be the same, or unlink it's called really. Will be the same across all file systems, but how you specifically change the bytes on the disk, that's specific to every file system. So that's also a sort of a driver. So in this homework, we are implementing a couple of device drivers. We're improving the console device driver so that it supports colored text. And then we're adding a new device driver called display, I think, that handles graphics display on the screen. I'll show the thing in action first. What did I do? Oh, okay, that's nothing. I have to be a little careful sometimes so I don't accidentally show the solutions on the screen. That's why I'm moving it back and forth. Okay. All right, so here it is. There's two programs. There's one called Pretty Print. So if you type Pretty Print, this is just a normal program, but the program is a little special. It makes a few extra system calls. It doesn't just print things on the screen, it makes some system calls to tell the OS what color it wants to print in. There's many different ways you could implement color support in a terminal. The way we're doing it is through a system call called IOCTL. Input-output control, really, IOCTL. It's a very common interface in any Unix. If you want to kind of manipulate a file beyond what you can do with normal files. So normal files you can read and write and seek. But if you have a pretend file like our display, you want to do something more. You want to change the resolution. What does it mean to, how do you change the resolution of a file? You don't really. So that was for I/O files, like a display. There's this I/O control system call that does this extra stuff, where you get to pass some parameters to the device and configure it. So with Pretty Print, it goes like this. Prints out a little rainbow of text, and now I'm typing something, and all these things are kind of important. So here, it's for every character, it's first specifying which color, and then it's doing a write system call to write it out. But now it says, please type something. And now it ought to come out colored. So now I'm typing hello, and it comes out blue. And so this is different because that's output, right? This output from the program being colored. Here's the input being colored. And those are kind of different pieces as we'll notice when we work through this. And now we go back, we get another and then, okay, that's it. So what's neat here is that we set the color. The pretty print actually says, it says standard in should have, let's see, how it go. I don't actually remember. Let's take a look at prettyprint.c in a bit. All right, and then, so that's basically all we need to get out of this. It'll take a little bit of refactoring of the code. There isn't anything complicated here. Like changing the color is very simple. But to get it to work across all the 4,000 lines of code we have here is actually a substantial number of lines that you need to change and kind of figure out how to do it right. All right, so the other one is the graphics driver. There's another program called imshow. If I just ls here, you'll see we have prettyprint, provided program. There's imshow, another provided program. You don't get to change these. Those are user programs. We don't do user mode programming here. Right? We're implementing the system calls to do what the user asked for. Okay, so here's the old console file we saw before. Maybe you recall we had this devs array that says, oh, for the device with major mode 3, I think that's the one, I'm not sure, we should use the console write function, right? Now we have another device, display, and we've set it up so that if someone tries to write to the display file, well, then it should show up on the screen instead. And we also have an I/O control for the display, so you can change the mode from text to graphics. So let's just see what it looks like first. Just goes like that, and then there was this little palette modification, and then it exits back to text mode. Right. This is actually one extra little piece here that you don't want to miss. See how the text is still there? When you switch modes, the screen gets emptied. And so if you didn't do anything special here, all that text would be gone, because now the text buffer is all zeroed out. So you want to save that away. Let's just see if there was anything I was missing in the description. Come on. All right. Right. So you've got it all here. Yeah. Okay. So we haven't really talked about virtual memory yet, and we'll get there in a little bit. But the thing that you only need to know right now is that the graphics mode video buffer is no longer at 0xA000. It's at kern base plus. Kern base is a global symbol that you'll have that's available everywhere. So just write anything to there, and you'll be fine. Okay, so let's just see then what the prettyprint and the imshow look like, so we get an idea of what we're dealing with. So this should actually be safe without me checking out hw3, because I'm not changing prettyprint or imshow, right? But just in case I make a mistake. All right, so prettyprint says here, set the color to, that color, and then print out one character. Change the color to another color and print out another character. And here we're saying, oh yeah, maybe at the very top here, we're printing a little bit to standard error, standard out, and to standard error, and they come out in different colors. So you can't have a global variable that's just storing the color, because the color is based on which file descriptor we're writing to, really. There's a standard in, also has its file descriptor, or maybe it's not standard in, it's like the global console color. But then each output file descriptor has its own color that you need to track separately. So you'll want probably to keep that in, there's a struct file, that's an open file descriptor. Really. So if you put the color in a struct file, then you'll be in pretty good shape. All right, so as you can see, right, there's a whole bunch of these system calls where we get instructed into like which color should the text have, right? And then we just write as normal to it, and the text comes out in that color. Okay, if we take a look at imshow, yeah, so all that blinking with the red, that's this. So there isn't, it looks like a lot of code, but it's basically just to figure out which color to use. So don't worry about that part. The important bits are here. Need a way to switch mode to the VGA mode. There's actually a function already provided for you that's called VGA13. So it'll let me make sure that's what it's called. Oh, j.h is all you need. Right. Okay. VGA mode 13. You call that, it switches over to the graphics mode, and then later on switch to mode 3. Now this doesn't save away any contents, sort of thing. You'll have to deal with that. And here's a set palette for the flashing bit. So actually talking directly to the graphics card, you don't have to worry about. Now why do I do all of that work for you? Let me show you. This is what it took to get VGA card to do, like, switch from one mode to another. And then all of this junk. Very opaque stuff. Right. So this write 3C4, what's it doing? It's writing to port C3C4. Nothing special about that. But then it's writing a couple of values. And you have to write them in a certain order for this really arcane VGA adapter to do what you want. So there was some electrical engineer who thought that this was easy to do from the electrical engineering point, and I don't care what the interface to the software engineers looks like. So then you end up with this garbage. And of course, there's no point in you kind of dealing with this. Back in the day, VGA was a pretty cool mode, because it can support all sorts of screens. Now we have these nice LCD screens. There isn't much to worry about. Back in the day, there was this cathode ray tube, a little radiation tube going that lights up the phosphorus kind of layer on the front of the display. And if you set these wrong, the whole display would break. That's also a nice part of the interface. Of course, now you can't break it. This is all just logical. But anyway, it's a pain in the ass, mostly because this is the palette, the standard VGA palette. That's okay. And here's the font. All right. It's an array with all of the pixels that make up the characters for the text mode. So the driver actually has to supply that as well. Of course, I didn't write this. I mean, I found pieces here and there, but it wasn't trivial to get it going. So you're provided that. What we need to worry about is the IOCTL system call. So let's take a look at the overall structure of some of these IO system calls. I think let's start at sysfile. I think you'll see that there's many. There's a few different files that start with the name sys. Actually, the two main ones seem to be sysfile and sysproc. The sysfile deals with system calls that take a file descriptor or a file name as parameter. Right? And this is, so write and read, for example. proc would be things that deal with processes, so fork, and exec, and exit. Actually, exec is a little bit of both. So that may be in sysfile. Because exec takes a file, right? That's the program we want to run, but it also runs does a lot of process manipulations. I'm not sure which one that is in. And syscall just provides the sort of the overall the infrastructure for making syscall. So syscall.h, just the numbers for the various system calls. Syscall.c is just like, oh, how do I get arguments from the registers? And given a syscall number, running the actual system call function. So this is generic for everything. When we end up implementing a new one, I don't think we were supposed to make a new one, or maybe we were. It sure looks like it. Let me see. IOCTL. Yeah. Okay, where is it? I don't see it. Oh, it's there, right there. Okay, good. So this time around, you provided a system call implementation already. Unfortunately, it doesn't do much. Let's take a look at sysfile.h. Let's see. So here's IOCTL. Every one of these system calls, there's a whole bunch of different system calls, right? They all have a wrapper function like this. They say sys underscore, and all it does is nicely pull out the arguments from the stack. So they're no longer sitting on the in the registers, right? Because we've gone through hundreds of lines of assembly already. That's all overwritten, but the parameters are hiding in there in the trap frame. Right? When the system call just started, we created the trap frame with all the register contents. These functions pull out the correct values out of the trap frame. The way it works is you say, oh, I want the 0th argument. So that is going to be, what was it now? RSI, I think. So that's the first the first value. It's always a 64-bit register, of course, but that'll either be a pointer. In this case, it's a pointer. FD. No, in this case, it's a number, but it corresponds to a pointer in the end. So we get a struct file out. Let's take a look at how that works. And then we get a couple of integers out. They're sitting in these local variables. And now we can make a normal system called file IOCTL. Of course, is also not part of XV6 normally. That's also provided. So let's see what that looks like. And here it is. So now, if we got a call in, a system call on any file, we see, oh, was this a device file? It doesn't have a major number. Console, if so, call this console IOCTL. Any OS code ends up being a lot of this. There's a lot of this, like, what's it called, kind of dispatch, I suppose, or demultiplexing, where you figure out, oh, what is the code we actually want to run? You'll see a lot of different ways to do it. Here we have a switch statement. In this other part with a devsv, right, there was an array and an index into it with function pointers. Different ways to do it. Let's take a look at console IO control. Here it is. So here it just says, I don't know what you're talking about. Right? And that's because, of course, this is a template. So this is not really an error. Right? You're supposed to fix it. You make it so that if a console IO control request comes in with the right parameters, the color changes. So start by, in here, maybe storing the color somewhere handy, probably somewhere in this. And then start worrying about how to change the output so you have a different color. One little hint. Let's see. We talked about this before. CGA_C is what puts a character on the screen. That is what controls the, actually that is what controls the color. Right. So here we're saying put a C in the lowest byte and then put 07 in the upper byte of this word. If you put something other than 07, well, then you'll get a different color. So that's where you kind of want to start. So you have to figure out how to pass in the right color, of course. And once you try to pass in a color here, well, whoever's calling this function has to have the right color. And up it goes. All right, I wanted to look at one more thing. What happened with that file? So let's see, we were in file.c. Right. Oh no, that wasn't it. Sys file. I should always just use Emacs. All right, so there was this thing here. So we get a struct file pointer out from the stack. But the user doesn't have, like the user is passing in, if you remember, the user passes in a number, right? 0, 1, or 2, saying which one are we changing our color on. So how does this argfd end up with a struct file pointer? Because 0, 1, or 2 clearly is not a pointer. Well, 0 would be a null pointer. 1 or 2, I don't know what that would be. So that number, 0, 1, or 2, is an index into proc.h struct proc here. And this is everything that our process knows about. Right. This captures the entire state of the process. One of those things are which files does this process have open at the moment. Every process normally has standard in, standard out, and standard error open. So 0, 1, 2 are already populated in this array. So this argfd, it sees, okay, I got a 1 in RSI. That means I want the second entry in this array, and that's the struct file that we're returning. So if we look at a struct file, just to kind of get in there a little bit, that's a struct file. An open file has these characteristics, right? This is a pointer to the actual contents. But it's also, oh, this could have been a pipe kind of file, right? Standard out is often a pipe. It could have been an actual on-disk sort of file, whether it's a device file or a normal, like actual block contents file. I don't really know what this is supposed to be. Yeah, it's sort of an equivalent of a null somehow. I don't know where they use that. But anyway, so now we have a pointer to, for a normal file, we have a pointer to the contents, and we'll see in much greater detail a month from now, like how that all works in the file system. But we also have an offset in here. Anyone want to take a guess at what the offset means?
Current index in the file.
That's where we are at the moment in the file, right? Because an open file is not just, this is the image. We've read the first 100 bytes. That means when we read the next byte, we should get byte 101. That's what an open file is. So it's called struct file. Maybe we should call it struct open file. I don't know. This is how it is in Unix, so we'll just stick with the naming convention. Right. Okay, so whenever you, and this actually, let's see, is it important now? Yes, it is important even for this homework. So now you're going to get, let's take a look at imshow again. You get this sort of thing happening. The program has opened this picture called cover.raw. It reads in from the picture 1,000 bytes, and then it writes it out to display. So this part clearly is already provided, like reading from files. Obviously the kernel knows how to do that sort of thing. We have all sorts of programs that do that. And now we're writing to this other open file called display, but it's a special display. It's a device file. Sorry, it's not a special display, it's a special file. It's a device file, and we discover sort of a few steps into this write system call, we discover that, oh, it is a device file of the display type we should be calling display write. None of this actually exists yet. So we get a write, sys write, and then maybe file write, and somewhere in there we see, oh, it's a device file. Display has a device major number something. Oh, what do we do then? We already had a console write. We knew how to deal with that. Now we have to deal with a display write and call a new function called display write. So basically what we're doing here then is we need to write those 1000 bytes into the video buffer. The video buffer, we know where it is in memory. Current base plus 0xa0000. So it's just a question of implementing a display write function that takes that buffer, the length, writes it into the right part of the picture, the right part of the display. So that brings us back then to this off. Because the first time we write to the display, we should be writing at the top of the screen, first kilobyte. But the second time we write, you see there's no difference. The buff didn't change, the FD didn't change, and the 1000 didn't change. And so the only way we know that we should write the next 1000 bytes is by looking at this off. So you'll have to increase the off, unless it does that on its own, I'm not sure. We have to make sure that this offset value is the way it should be, and use it to write to the right place in the display memory. Okay. Any questions? Right. So the console bit is almost all provided. It's a question of changing a couple of functions so that it accepts these colors. And then we're implementing a new device driver entirely. It doesn't exist at all. So you want to look at how console works. Like this device file, I think maybe that one exists. Probably. But after that, there's nothing else. So you'll want to see how is console.c implemented, the initialization of the console write, how does that work? How is console sort of plugged into everything else? Wherever else there's a reference to console something, you want to see, oh, should I be doing something like that for the display too? Right. Clearly for printf you don't want to do, or for cprintf you don't need to do anything for the display. We're not dealing with that. We're just doing pictures, but in many cases it's going to be like that. So let's, for example, take a look at main.c. See, there's a console in it. You'll probably want a display in it right next to it. All right. Let's see what console in it does. Right. So it's setting up in this array. It's setting up. How do you write to the console? How do you read from the console? And we don't need to set up any interrupt handling for the keyboard when we're doing a display driver. Right. Okay. I think we'll leave it at that for now. Hopefully you'll have lots of good questions at the next lecture, because this is. It's not that it's a complicated homework. There's really no magic here. What's hard is that you're suddenly dealing with 4,000 lines of functional code, complicated functional code, and you're doing some surgery on it. So you'll probably do well to bring some questions on Thursday. All right. With that, I think I want to change the topic a little bit and continue discussing the operation mode. So we talked about real mode, 16-bit. We got into protected mode last time. But we really only got to discuss the difference between supervisor and user mode operation. Right? Privileged instructions in super user mode, in user mode, supervisor mode, sorry, and in user mode, basically only accessing memory and issuing system calls. The other part of protected mode that's really important is paging. So there's it's called virtual memory sometimes. It's called paging. It's called, what else is it called? There's at least another couple of names for it that I can't recall now. But anyway, the general idea of paging is something like this. So we have, let's make this a little bigger. Really? Okay, so let's have a pretend machine here that has a small amount of memory. Each one of these, we call these page frames. To be very explicit, we can call them physical page frames. Oftentimes, they just go by the name frames. This is just regular memory. It's what we were dealing with in real mode. Pages are always 4 kilobytes long. So each one of these, 4 KB of RAM. Okay, so this is regular memory. If you use, without paging, without virtual memory, if you dereference address 0, you read from here. Right? Address 4 kilobytes, it's here. 4 kilobytes, 500 bytes, well, it's somewhere in here. So I should use this pointer. Okay, so the offsets here are clearly 4 kilobytes, 8 kilobytes, 12 kilobytes, and so on. Now the problem with physical memory, well, there's a couple of things here. If you want to share RAM between two programs running at the same time, chances are they both want the same address. Like they both want to start at address 0. Or maybe if they're really clever, they might have kind of made some prior agreement that, oh, I'm going to use addresses from 1 megabyte and up, and you can use from 0 to 1 megabyte. It starts getting really complicated, especially if you don't know which other programs are going to run on the same machine, which is usually the case on a general purpose computer. The user expects to just be able to load any program. With segmentation, it was possible for a little while to kind of get around it, because now you run one program, you put the segment, the code segment, you put at 0. And then when the kernel, there weren't really any proper kernels back then, but when you want to switch programs, if you're switching quickly between programs that are running at the same time, you could change just the CS and the DS. Say, stop pointing at 0 and put them up here. So now, if the program itself doesn't manipulate CS and DS, well, now all of its pointers are going to work just fine running up here instead. And that works okay for a little bit, but it's not a very generic solution. So the generic solution is this paging business. Here, every process, okay, call this a per process page table. So with paging, every process gets to control its own memory layout. Every process has address 0. Every process looks the same essentially, or its memory looks the same to it. The way this works is we have a page table with a bunch of pointers in it. And these are 64-bit entries. They're not 4 kilobytes. All right, actually, let's do it like this. And then finally, I guess we have the process virtual memory. And that's also in pages. Okay, So this should be clear pretty soon. So the process has this, the view the process has of memory is this thing called virtual memory. It looks to it like the only things that exist in memory is really the process's own code, and then maybe some kernel stuff higher up, which we'll see later on. But in reality, it's really all over the place in real RAM. So the way this works is if the process tries to access the 0th page, like bytes 0 through 4095, the processor looks it up in the process's page table, looks up that address, and sees, aha, this has a, let's call it a 4 in it. So this says, all right, the 0th page in the process's virtual memory, let's call it, usually we call them virtual memory pages and physical page frames. But if you just say page, it usually means this. If you just say frame, it usually means this. They're the same size, but they're slightly different things. So here, if you access anything in the 0th virtual memory page, the processor looks it up in this per process page table and sees, oh, it's page frame number 4. So you're actually going to access this one over here. So what looked like, say, move 10 into EAX, RAX over here, ends up being move 10 plus 5 times 4 kilobytes, 10 plus 20 kilobytes into RAX. That's actually what it does. This happens for every memory access. So all of execution, essentially, both for the kernel and for the process, is always indirect like this. It's a constant looking up in this table to see, oh, which address did they really mean? Because memory is always like this. Physical memory doesn't move around, right? But virtual memory is extremely flexible. So what we end up having is perhaps, I'll say, something like this. And for the rest of them, it's all zeros. So now, let's see if I kind of get it right here. Is that number 7? Maybe. Yeah. Okay. So now you kind of take a jumble of these pages, 3 pages in random locations in memory. By putting 3 values in this page table, now suddenly it looks like one contiguous range of 12 kilobytes of RAM. This is really elegant because now you can dynamically allocate. Say we started out with a heap that was 12 kilobytes. I'll draw a new one. So our heap initially was this big, right? And now malloc comes and says, SBRK, I need some more memory. Then we can, as the kernel, we can say, okay, fine, you can have another page. If we just need another page, all we need to do is put a new number in here, 5, which in essence is a pointer like this. And now we're set. Now we've allocated for this process, for this layout, we're saying, okay, you should be reading, if they start accessing that part of memory, well, you should be reading from this physical memory page. So how does this work if you have 2 processes? Well, it's the same thing. Oh. Actually, I should go the other way around. Let me copy this one instead. Right, so here's another process. Of course, it can't have the same numbers in here, because then it would have the same code and the same data, and it would get really awkward. You had 2 processes modifying each other's globals and that sort of thing. This doesn't work. But what if we go with 15, 1, and 6, and 3, right? Now you have 2 different processes. They both, to them, it looks like, oh, I can access address 0, But in fact, if you access address 0 in process 1, you're going to be accessing that byte, right? And if you're in process 2 and you access address 0, well, then we're on here. We're reading this byte. Okay, of course, there's some complication here. Like, how does the kernel know which page to use? Like, which pages are free? You can't just take any number. And that's a kernel memory allocator. And whenever you free something, we need to put it back into the memory allocator. And what happens when you run out of memory? If there isn't another page and the application says, give me another one, then there's ways to deal with that too, but I think we'll save that for another day. That's basically saving page contents on disk. So this is a very powerful abstraction, but it looks like it's really slow. Right? It used to be one memory access, but now suddenly it became, look it up in this array, that's at least another memory access. So it looks like 2 memory accesses for every one, so is it going to run half the speed? What do you think? You do twice the work, right? How can we make it faster?
Totally lucked out because when you do, you grab a page and you cache it, so then you're going to keep reaccessing the same spot locally.
Caching is a good thought here. Yeah, it's actually called, so this page table actually has a dedicated cache. It's called a TLB, Translation Look-Aside Buffer, and don't ask me why. But basically for each one of these entries, for recent entries, it's sitting in that cache, and it's an extremely fast cache. So in the end, that little translation doesn't cost much. I think there may be a slight cost in the virtualization, even if you do local memory accesses, but I don't know how much it is. It probably is less than a cycle, on average. Right. There's another cost. The page table itself. We need one of these for each process. So it's actually, you'd think, oh, you can just use a hash table or something. It'll be fine. Right? But we want this to be really fast. It needs to be a really simple structure because the hardware needs to have a cache of it. It should be easy for everyone to deal with. So no complicated data structures. What's the size of this thing, do you think? Like, how big is a page table? How many entries do we need in a page table?
However many bytes there is divided by 4 kilobytes.
How many bytes of what?
The physical RAM divided by 4 kilobytes.
It's not physical RAM, unfortunately. Virtual memory has a range that depends on the address size of the machine. So on a 32-bit machine, there's 4 gigabytes of RAM that we need to be able to represent. So we want to say for any page in those 4 gigabytes, that means 1,000,000 entries. Right? 4 giga divided by 4 kilo, that's 1 mega. So we need 1,000,000 entries. How big is an entry? Right, on a 32-bit machine, it's actually 32-bit entries. So that's 4 bytes. So now we're stuck with 4 megabytes worth of page table.
That's
Per process. All right, and the process could be something like cat. Process is like 2 kilobytes long, and now we have 4 megabytes of page table. In fact, we may not even have that much RAM in the machine. So this doesn't work. We can't have just a big flat array, at least. We need something a little bit more clever. It gets much worse on a 64-bit machine, right? Because now the address range is 64 bits, and that's for let's see. So it's 1,000,000 entries for 4 megabytes, and then there's 4 billion million entries, right? That's how many we need. So there's not enough RAM even to represent the page table ever in these machines. So we can't do it that way. All right, so let's take a quick look, and I'll just start with the 32-bit because it's less complicated, because it's not so many pages. Okay, first of all, when you're running a process, before you start running a certain process, you point this special register, the CR3, control register 3. You say, oh yeah, this is the page table you should be using. Right? That's how it all works. So you tell the processor, before you start running the process, you say CR3 equals that. And now from now on, the processor knows it's going to look it up in that table, right, whenever you do a memory access. Okay, so the overall structure looks like this. We have a page directory, it's called, which has, actually, let me just copy my beautiful stack here. There's a page directory that has 1,024 entries. And each one of those entries points at a page table, which has another 1,024 entries. Right, so from each one of these, there's a pointer to a page table. Let's just make 2 of these page tables to make it a little more clear. Like that. Each one of them has 1,024 entries. It's 1,024 entries because every entry is 4 bytes. So now in a page directory with 1,024 entries, that becomes 4 kilobytes. Everything works in 4 kilobyte chunks. Same thing with the page table. It has 1,024 entries, and each page table entry points at a page. 1,096 byte page. Now actually, physical page frame. Right. So now, if you want to access, I should probably move these down. It's more common that the zeroth and first entry are filled. So now if you try to access the first entry, the first page in the page table, it's a 2-step process for the processor. It's getting worse, right? In one sense, it's getting worse. First, it looks into this directory with only 1,024 entries. It's not 1,000,000 entries, which is great. So it looks in that page directory, sees, oh, it's in the first page table. So it goes and looks in that one, and you wanted the first entry in the first page table, so that's going to be this one, and that finally leads you to which page to access. So it used to be in the sort of the conceptual view we had, there was one extra lookup in the page directory, in the page table, and that gets us to the actual memory page. But in order to make it a little more efficient, we have this 2-level structure. Why do you think a 2-level structure is more efficient? Now it seems like there's double the work.
You don't have to allocate all the other ones.
Right, exactly. So if no one's using more than these 2, each one of these actually represents 1,000 entries, each being 4 kilobytes. So that's 4 megabytes in each one of these chunks. So if you don't use them more than 4 megabytes, well, you don't need an entry here or there or there or there. That means you don't need to allocate that whole table. So now you have 4 kilobytes for that one, 4 kilobytes for the first one, and then however many page frames you allocated in the first page table. So for a small process, it's a small page table. If it's a huge process that uses 4 gigabytes of RAM, well, then it's a megabyte worth of page table, but we can live with that. It's a small percentage of the overall memory. Okay, we're out of time. I'll just, as a brief preview, when you do this in 64-bit, there's not enough entries, right? So how do we do it? Well, we just use the same model. So now we have 4 layers. It's called I don't know why it's called a PML4, that's the first one. And then you have the page directory pointer table, and then the page directory, and then the page table. So there's 2 extra layers stacked on top. And even that doesn't give us 64-bit, that only gives us 48-bit worth. But we'll get to that next time. All right, please get started on the homework so we can have some good questions about it on Thursday.